Hi, the topic we are going to talk about today is really important in this course and also in computer science. We are going to talk about proof by induction for naturals. Actually, induction is a proof technique that can be used on any data type which satisfies recursion and accept recursive algorithms and recursive definitions. And actually, it is really similar to what we had in the fifth axiom of Pinot. If you remember, even when we stated different versions of that fifth axiom, we talked about induction. So how we can use induction is that we know that we have a data type which accepts recursion. For example, here in this lecture, we want to talk about and cover that for natural numbers, because for natural we have like that definition and we have that understanding based on the axioms that we have. Okay, what happens is actually similar to the nature of natural numbers. I know something is true for some small number or for a smallest number which we call base. And if we know for any arbitrary element there, if that statement is true, then it is true for the next one. If I can show by knowing this, I can show this for the successor of that, then I can say I can cover it for everything. Because it is like what happens in natural numbers. I know 0 is in natural, so when I show a statement is true for 0, I'm done with that. And I know if that statement is true for some arbitrary element in my natural number, then it must be true for the successor of that. Then I can say it is true for all natural numbers. The reason is that, okay, I tested that, I know it is true. So I can say, since it is true for that, and since I know if it is true for some arbitrary element, it is true for the successor of that, I can say, okay, I go to 1 and it is true for 1. And I can go to 2 and it is true for 2, because 1 is one element in natural number. And I know if it is true for 1, then it must be true for 2. And by doing that, and since I know if I start from somewhere and keep taking successors, I'm covering everything. It is like I'm covering that statement for everything, or I'm saying that that statement is true for every element in my set. So what happens in natural number and for the induction on natural number is this. I have a predicate. That predicate have one free variable, and that free variable is of type natural. What I do is that if we show P of 0 is true, and for all x, P of x means P of x plus 1, we can claim for all x, P of x is true. So what happens is that we know what a statement we want to talk about. It is P of x, it is our predicate. And then we show if it is true for P of x. It is the first step, we call it base case. The reason that it is base is that 0 is the least and minimum element in natural numbers. And then if I can prove that for all x, P of x implies P of x plus 1, then I can claim that. Okay, let's see what actually it means. When we talk about universal quantifier and we want to show that for some predicate, we have these predicates and we want to apply that universal quantifier, then based on the nature of universal quantifier, we can take any arbitrary, because I said, okay, I don't care what, but if I take that, it happens. So it happens for everything, because I could choose something else, right? So I choose something or some arbitrary element x, and what happens is that I assume P of x is true Just assume, I don't prove that. And by this assumption, I need to show P of x plus 1 is true. You remember when we had P then Q and we wanted to show that it is true, if this part, which is my premise, is false, I'm done. Because for any false premise, the whole conditional statement is true. So the challenge is when this one is true and I need to show if this is true, then this one must be true. Because the only case that the conditional statement is not true is that the first one is true and the second one is false. The consequence is false. So it is the reason that when I want to talk about this conditional statement, I assume it is true and show, okay, if it is true, then this must be true. And what actually happens is that I already showed that for something, and I know that there exists something, one element in my natural number for which it is true. So when I show P of 0, I say, okay, for 0 the statement is true. And since it says that if P of x is true, then P of x plus 1 is true, I can say, okay, it is true for 1, and it is true for 2, since it is true for 1. And then I can continue over and over. It is what happens. And so the most important part of what I wrote is this part. It is what we need to do. We need to show base case. It is really important because we need to substitute that a small number in our statement. And the second part is the more challenging part. Again, assuming something is true for x is really easy. And when we want to show P of x plus 1, the good thing is that P of x plus 1 and P of x are really similar. So it is like I can do something on P of x and find P of x plus 1, or expand it to find P of x plus 1. We can see that in one example that we want to talk now. Okay, before showing the statement, I want to create a statement myself. So what I want to do is that I want to start from the minimum odd number and start adding consecutive odd numbers. So if I have 1 and only 1, I can say it is equal to 1. What happens if I add the first 2 consecutive numbers? The addition is 4. What if I add 3 consecutive odd numbers starting from 1? It is 9. 1 plus 3 plus 5 plus 7. It is 16. 1 plus 3 plus 5 plus 7 plus 9. It is 25. It seems that I see a pattern here. On the left column, I'm adding some consecutive numbers, actually x consecutive numbers, consecutive odd numbers starting from 1 and adding x consecutive odd numbers. And what happens on the right column is something like it is x squared. For the first one, when I have 1, it is 1 square. When I have 2, it is 2 square. 3 square, 4 square, 5 square. And I see something. I cannot prove that it is true for all naturals by just testing, right? I cannot write that and compute the addition for all the possible consecutive odd numbers starting from 1 to see if it is happening or not. So what I want to do, I see that pattern, I want to see if I can prove that pattern. So what happens is that I create that predicate P of x. The summation of first x consecutive odd numbers is equal to x squared. Now I have my predicate with x, so it is like a statement which has that variable x, and I want to prove that for natural numbers. First of all, the first step is base case. Base case, we learned that in natural numbers is for 0 because the minimum number, the smallest number is 0. So I need to show for the summation of first 0 consecutive numbers is 0 square, which is like, okay, the summation of 0 numbers is 0, 0 square is 0. It is really easy. So I can check that. If you want, you can do something with P of 1 as well, just to like make sure you're doing something. But base case for even one of them is true. I mean, for the base is true. So first means that the summation of first one consecutive number, odd number, which is 1, is equal to 1 square. So we see that for P of 1 is also true. We actually saw that. We have that. Okay, for until 5 we have all of those. Okay, what happens in the next one is that we assume P of x for some arbitrary x which is our induction hypothesis. And next, we want to prove P of x plus 1 is true. And since you see that here, I assume, so it is hypothesis here, we want to prove, so it is induction goal. We call these two steps, which is actually for all x, P of x implies P of x plus 1. We call this part induction step or inductive step, which has one hypothesis part and one goal part. So by assuming that hypothesis is true, if I can show the goal is true, I am done. I can show that it is true for all x. Okay, we assume P of x for some arbitrary x, which means that we assume the addition of first x odd numbers is x squared, which is actually 1 plus 3. So what is like first x odd numbers? So it is like continuing from 1 plus 3 plus 2x minus 1. You can find why I say that. Yeah, let's see. The first one is 1. The second one is 3. The third one is 5. So the x1 must be 2 times x minus 1. You can find that yourself, and I assume that it is true. I don't need to prove that, I just assume that. And part 3, which is more challenging and is my goal, is that we want to prove P of x plus 1, which actually shows that 1 plus 3 plus 2x minus 1, it is the x odd number, but I need x plus 1 odd number as well, which is 2 more than that. And I want to show that it is equal to x plus 1 squared. This is what I want to show. Okay, based on my hypothesis, I write it as IH, which stands for induction hypothesis. I can say 1 plus 3 plus 2x minus 1 is equal to x squared. So actually I can say plus 2x plus 1 is, okay, for this part I have a value. You see that here and you see that here, but this part is something that we accept is true. We have it as x squared. I know based on hypothesis the summation on the left hand side of my statement is x squared plus 2x plus 1, which is actually really easy to see that x squared plus 2x plus 1 is actually x plus 1 squared. And we are done with showing that p of x plus 1 is true. Okay, we took one arbitrary element x, we assume the assumption, we assume the statement is true, the predicate is true, and we show that it is true for the next step, which is x plus 1, or successor of x, which is x plus 1 in natural number. Okay, by doing that, I can say, okay, for all x, for all natural numbers, the summation of first x consecutive odd numbers is equal to x squared. It is how proof by induction work, and in the next video we are going to see some more examples.